Hey, everybody, and welcome back to another episode of Adventures in Machine Learning. I'm your host, Charles Max Wood, and this week we're talking to Annie Didier. Now, Annie, you're kind of doing some interesting stuff. I got introduced to you through Chris Mattman, who we had on a month or so ago, and yeah, I love getting people on who are like, I'm just going to say you're a rocket scientist because it makes it fun. No, it's true.
Really not.
You didn't work on the rockets.
There are actually very few people NASA JPL who are rocket scientists.
Yeah, fair enough.
It takes a village.
Yes, it's so true.
to build the rovers. So yeah, I am a data scientist in Chris Mattman's group, and I was thinking today we could talk a bit about computer vision and Mars, because those two things are my jam. I've worked on some other stuff at JPL as well, but those things are by far the coolest. And I think everyone is pretty excited about Mars right now because the Perseverance rover just landed. And so I'm ready to nerd out about Mars.
Awesome.
I remember working my tail off to become a senior developer. I read every book I could get my hands on. I went to any conference I could and watched the videos about the things that I thought I needed to learn. And eventually, I got that senior developer job. And then I realized that the rest of my career looked just like where I was now. I mean, where was the rush I got from learning? What was I supposed to do to keep growing? And then I found it. I got the chance to mentor some developers. I started a podcast and helped many more developers. I did screencasts and helped even more developers. I kind of became a dev hero. And now I want to help you become one too. And if you're looking forward to something more than doing the same thing at a different job 3 years from now, then join the Dev Heroes Accelerator. I'll walk you through the process of building and growing a following and finding people that you can uniquely help as you build the next stage of your career. You can learn more at devheroesaccelerator.com.
Well, just for the record, my grandfather worked on the rocket boosters for the shuttle. So
way cool. So you do know an actual rocket scientist.
I did. I grew up around one. So yeah.
That's amazing.
Yeah, but it's funny too because he wasn't a scientist in the let's make this thing go up. He was a scientist in the hey, one of these blew up and let's make sure it doesn't blow up again.
Well, those are equally important people to have on the team. You definitely need those.
Yeah. But he built a machine that used a laser to check the inside of the booster to make sure it was clean before they filled it with fuel.
Oh, cool.
So anyway, so that's my claim to rocket science fame. But anyway, let's talk about Mars.
Yes, Mars. So I'm going to tell you a bit about a suite of algorithms that I worked on in a research and technology demonstration. So to be clear,
hang on, I'm getting popcorn.
So to be clear, these are things that are not on Mars yet, but we hope that someday they will be. And we have shown in our tech demo that they could be. So there are a few different algorithms that were developed in this tech demo. I'll focus on one, but give you kind of like a broad overview of the things that we were working on. So this tech demo was to demonstrate that or how we could use deep learning algorithms on future Mars rovers. Now, deep learning algorithms are not on rovers now, and that's because of computational constraints. I think that a lot of people don't realize this, but the, computers that are on the rovers are very old and outdated compared to our technology now. So we were doing this tech demo for the next generation of space compute chip, which has about the power of your mobile phone. And we're hoping that that will be the next thing that goes up to space eventually. And so right now, the things that run on our rovers are maybe have the power of like an old iPhone or an iPod, excuse me.
Wow.
Yeah. So, and the reason for that lag is a couple of things. So everything that we send into space has to be radiation hardened. You know, we have very unique environment up there and subject to a lot more kinds of just physical bombardment than we are down here. And then the other reason that technology lags behind is, we're sending these $1 million rovers up into space, and we don't want to be cutting edge. We want to use something that we know is going to work. The computer is not the part that we want to take any risks on. So hopefully we will have a computer that is as powerful as your iPhone soon on the rovers. So we were demoing this suite of algorithms on this next generation of compute chip, and they do a few different things. So one of our algorithms is called Spock. It's the
nice.
We intentionally named all of our algorithms after Star Trek characters. We're
there you go.
So it's the soil property and object classification algorithm. And
okay, there you go. Yeah, because it's a government thing and it has to have an acronym.
It does. There's so many acronyms. I actually have a colleague who built a tool that just will look up all the NASA acronyms for you. It's called Acronyms Seriously Suck. It's a great little tool.
Also an acronym.
Also an acronym, yeah. So this algorithm, Spock, what it does is it's a convolutional neural network that takes in an image from a rover's navigation camera, NavCam, and then classifies each pixel with the type of terrain that it is. So that can be things like sand or hard rock. And the reason that we want to distinguish between those things is because it's much better for the rover to drive on a hard rock surface than it is on sand. We really have a problem with sand, and we don't want our rovers to get stuck in sand.
And I read this documentary called The Martian.
Yes, I have also read that documentary.
But yeah, he gets stuck in some deep sand, right? And has to figure out how to get Yeah.
There's another algorithm that we developed in this group that I worked on just very tangentially called Viger. And I'm sorry, I don't remember what that one stands for.
Star Trek 1 was where that's from. The first movie.
We tried to stick pretty much to the original series for our naming. But this one works by looking at the terrain features, again, from the navigation camera, and tries to predict how much energy it will take to drive over all of those different surfaces. So that's also useful in navigation and optimal path planning.
Oh, that's interesting. How far out does it look?
Just in front of it,
So just whatever it can see.
Whatever it can see in its field of view with the nav cam, and I don't know how far that is. So
yeah.
So it's good for local path planning. Actually, I don't know if they have done this, but we do have orbiters as well that could see over the rover and further out. I don't think that's what we use though, because of the resolution. And then the algorithm that I'll talk to you about the most today is the one that I worked on, Scotty, science captioning of terrain images. So all of these things can be helpful for navigation, but the algorithm that I worked on in particular was meant to facilitate science and to help overcome the data downlink limitation. So the issue
the data downlink limitation, let's just start there.
Yeah.
What are we looking at?
That's what I want to explain. So the rovers are able to take far more pictures than we can ever possibly retrieve from them. And that's because they have to send those messages through space, and they are constrained by the laws of physics, as well as the availability of relay orbiters and availability of the Deep Space Network. So we have about 5 spacecraft. We have 5 spacecraft in orbit. 2 of them are what is primarily used to communicate with the rovers. Some of the other ones are owned by like ESA, the European Space Agency, and are available for like emergencies only,
Mm-hmm.
So rovers can communicate directly to Earth via X-band communication. And they do that sometimes, but by and large, science data is way too big to go through a direct communication from rover to Earth. So we rely on these orbiters that pass over the rover, and the rover will uplink its data to the orbiter, and then the orbiter will send its data to us. Now, we also have limitations in the frequency with which we can do that, because the orbiter has to see the rover and then it has to see us. And so there are only like 1 to 2 times per day that the orbiter can communicate with the rover.
Well, can we do that with Twitter? I think my life might get
Yeah, right. Okay, so now let's talk data rates, just to give you a better sense of like how much data we can actually send through space.
Mm-hmm.
Now, the direct to Earth data, so from rover to Earth, varies from about 500 bits per second to 32,000 bits per second. To give you some sense of what that means, that's about like roughly half as fast as a standard home modem.
Oh, wow.
Yeah.
You mean not the cable modem I'm talking to you on. We're talking
like old modem.
Yeah, the old time.
Remember the original internet? Yeah. So now the data rate to the Mars Reconnaissance Orbiter is selected automatically and continuously during communications, and that can be as high as 2 million bits per second. So, and the data rate to the Odyssey orbiter is selectable between 128,000 and 256,000 bits. So that's about 4 to 8 times faster than a home modem. Now, in terms of like downlink capacity, then from rover to orbiter to us, the Curiosity rover has a downlink capacity of around 500 megabits, which is about 60 megabytes.
Uh-huh.
So less than a gig.
Right.
No 5G here.
I know, you're on AOL.
Yeah, exactly. So we want some way to overcome this data downlink limitation. The rover is going to take far more pictures than it will ever be able to send back. And right now, the way we overcome some of that is we send back thumbnails, and then we see the thumbnails, and then the scientists will be like, oh, let's take that image and get a bigger version of that.
Right.
But there will still be things in between that are missed. And this problem is not going to get better anytime soon, because we're always going to be constrained by the laws of physics, And ESA's planned Fetch rover, as part of the Sample Retriever and Lander mission, is expected to drive even more than our current rovers. So our current rovers drive like really pretty slow.
Mm-hmm.
And this one is expected to drive about 1 kilometer per sol, which is about 10 times more than the average driving distance of the Curiosity rover. Right. So faster driving means more navcam images taken at constant intervals, because it needs that to navigate. And so potentially driving by a lot of interesting stuff that we won't be able to get back down. So our goal was to find some cool way to summarize what is in those images, and with a textual summary, because text data is much smaller than image data. So while you could never get back all of the images, you could potentially get back, say, an image caption from each of the images, and then get some kind of global summary of what the rover has taken images of, and then from there select. And you could go through the same process of like selecting thumbnails and then further down selecting to your larger images. So this is the model that I'm going to tell you how it works.
All right, let's do it.
Okay. So the Scotty model is a deep learning model that takes pictures from the rover's navcam and then automatically captions them with geological content. So the things that would be interesting to the scientists. That's things like a view of bedrock with veins running through it and sand dunes in the background, kind of like a human would write a caption for the image. And those things are important to geologists because they'll tell them things like whether there was possibly water there, or with sand dunes, that gives you some information about wind patterns on the surface.
Right.
So the model that we used is based on the Show, Attend, and Tell network, which is from a 2015 paper. So in deep learning terms, like pretty old.
Right.
we'll say pretty established. We like things that work well.
There we go. Yeah.
Yeah. So the Show, Attend, and Tell network is basically a convolutional neural network that is attached to a type of recurrent neural network called an LSTM with an attention layer. And I can go through each of these pieces if you like.
I was going to say, we've talked about some of these pieces, but it might be good just to give people kind of a thumbnail overview of what each type of algorithm is. And then, yeah, let's dive into how it all works.
Yeah. Okay. So first of all, just a brief overview of traditional fully connected neural networks. The way they work is they have some input layer, a hidden layer, or many hidden layers, and an output layer. The input layer can accept all kinds of different input types, and then the hidden layers perform calculations on the input or input from the previous hidden layers. They're made up of neurons, which have weights and biases, and each neuron gets some inputs, performs a dot product, and an optional nonlinearity. Now, and then all those neurons are connected to the neurons in the previous layer, and each neuron has its own weight. And that weight is the thing that makes the model smart, because the weight can update and it can, quote unquote, learn to give a final score, like some sort of class probability or a word, you know. Now, that type of network doesn't work well for images because since everything is connected to everything else, then every pixel would be treated in the same way. But with images and pixels, we really care about the pixels that are near to each other. We don't want them to be treated the same locally as the pixels that are far apart. So we use something called a convolutional neural network, which treats data spatially. So in this setup, instead of having hidden fully connected layers, we have convolutional layers. So if you think about the way that we recognize images, as an example, let's say recognizing a face. You know, we know that something's a face. We see like so specific features like eyes, mouth, nose. And then we're like, oh, all of those things are together. That's a face.
Right.
So we try to make a model that essentially does the same thing. So we have some image, let's say like 32 by 32. We can represent that as a matrix. And then with a CNN, we take a small filter, say 5 by 5, and slide that over the whole image, and it will detect a particular feature and create a feature map. So it will say, let's say that we have a filter that just recognizes eyes. So you slide that over your whole image, and then it will light up at like a particular spot that says like, here's an eye, or top left corner, there's an eye, or bottom right corner, there's an eye. And so then we do that with multiple filters so that we can pick up all different kinds of features. And then we stack those all on top of each other. So we have a map that says, this is where our eyes are. And another map that says, this is where the nose is. And another map that says, this is where the mouth is. And then we stack those, do another filter over that says, this is where the head is, and so on. So we're like combining features as we go through the network. Now, obviously, the network doesn't actually know that it's looking for things like eyes and a nose and a mouth, just like fully connected networks. They have weights that are learnable, and those filters kind of learn to pick up on things. And an image is typically like it learns to pick up on an edge or a gradient in color or like some sort of curve. And obviously in Mars images, we're not really looking for eyes and nose and mouth.
Or I don't know. I've heard rumors.
Yeah, or are we? For this particular particular model, we're looking for things like white veins and sand dunes.
Right. So it can say this is the top of a
A sand
geologic.
dune. Yeah. Or like
that this is the horizon, or yeah.
Yeah, exactly. So the CNN then outputs, like, at the very end, a feature map that gets flattened and goes into the next part of our architecture. So we used the VGG architecture, which has 512 of these feature maps. And our feature maps are 14 by 14. So then you flatten them at the end. And so then you get a feature vector that's 196 long, 14 times 14. And we have 512 of them. And then those are inputs to our LSTM, which is the part that actually creates the caption on the image.
Oh, cool. And so, LSTM stands for?
Long short-term memory.
Okay.
So I'll talk about what that means too. So an LSTM network is a flavor of RNN network, which just means recurrent neural network. So the recurrent neural network is a type of network that is used for sequences. So the CNN, good at images, RNN, good at sequence data. So this is used for things like language quite a bit because when you're building a sentence, the words that came before are important in determining the next word.
Right.
So you can think of a sentence as a type of sequence. So where you're building on the previous words. So RNNs have this kind of sequential memory, some knowledge about what came before. So like the first kind of network I talked about, just regular fully connected feed-forward networks, they have some input, a hidden state that has the neurons in it and does dot products on the input, and then it generates some output. But how does it get this memory? Where does that come from? So it basically just has an extra little loop in its hidden network that is the hidden state from the previous cell or term.
Okay.
So the hidden state from the previous step gets passed to the hidden state in the next step. Now, RNNs have a problem. And that's why we have some different flavors of RNNs to address this problem. We don't actually use like the vanilla RNN that much. So the problem with RNNs, now you'll remember that all neural networks have this weight term, right?
Right.
That is what's being learned. Now, with a sequential network, that weight is being multiplied by itself over and over again from the previous time steps. And so what will happen when you have some sequence, some values that is raised to the n power? As your sequence goes on, if that value is greater than 1, it will explode, right? So 2 times 2 times 2 times 2 times 2, it's going to get huge. Now, what if that value is less than 1? Then it will diminish.
Trend
it will get
0.
very tiny. And as we do back propagation, we're differentiating that function. And so we're still just going to have that same problem. So we need some way to modulate that value and make it so that it doesn't explode. So you might be wondering, well, why doesn't that happen in regular feed-forward networks?
Right.
And the answer is that it can, but it usually doesn't, because you're usually not multiplying like the same value by itself over and over. Throughout your layers, you could have some number that's bigger than 1. And then the next weight could be much less than 1. And so then they would kind of cancel each other out.
That makes sense.
So we need
this one has that fancy loop back.
Yeah, exactly. This one has that fancy loop back. And so you need some way to bring back in that sort of cancellation. So that's why LSTMs, long short-term memory, have this other thing in addition to like your memory cell called the forget gate. And so that is a way to bring in another additional weight that will help cancel out some of those other weights and kind of forget about older outputs.
I gotcha. That makes sense. It's like,
hey folks, if you love this podcast and would like to support the show, or if you wish you could listen without the sponsorship messages, then you're in luck. We're setting up new premium podcast feeds where you can get all of the episodes released after Christmas 2020 without the ads. Signing up will help us pay for editing and production, and you can go sign up at devchat.tv/premium.
It's like one of my kids. In fact, here, I'll tell you a short story, right? So I just got a new iPhone because the one I had wasn't recognizing the SIM card anymore, which meant I couldn't make phone calls. So I get this a new phone, right? And my 12-year-old thinks, oh, Dad's replacing his phone, which means I'm going to get his old iPhone.
Obviously, that's what that means.
So because my two older kids, the two that are older than her, have iPhones, and they got them because we already right, and we already had those phones, and so when we were like, we're going to give them phones, we're like, we're not going to go buy them, we're just going to give them our old phones. Yeah. So anyway. So she came down and asked my wife when she was going to get that phone. And my wife looked at her and said, when you start taking care of your stuff. And this is where this loop back feature happens, right? So she yells at my wife and my wife yells back. And then my daughter yells back louder, right? And so it keeps looping back until eventually and then the forget gate, she gets sent to bed.
Yeah. So you were about to have this exploding gradient problem,
right?
With the yelling more and more until she gets sent to bed. Perfect.
Right. Great analogy. And then she slept. And when she got up this morning, she's back to kind of the regular angry preteen. So
I would expect nothing other from a preteen. That reminds me, Mother's Day is coming up and I got to do something extra special for my mom to make up for my teenage years. I just feel like I spent most of my adult life just trying to make up for when I was a teenager.
Oh man.
Yeah. Anyways, so the LSTM, this is the part that actually captions the image. And so
gotcha.
The previous cell or state, is the word that came before in the sentence. And then it uses that information along with some information about the image to generate the next word in the sentence. So the one last thing that I haven't talked about yet is this attention mechanism. Because I said this is a show, attend and tell model. So that attention map basically uses the feature map from the last part of the CNN. So that's that 196 by 512 part, and produces a mask over that feature map that tells the LSTM which part of the image it should pay attention to for the next word.
Oh, that's interesting. I was going to ask because, it seems like one little set of pixels. Yeah. Is it in the lower part or the upper part? Because you said behind and in front of. So Is that what this is solving is?
Exactly. So like, for instance, the attention part will light up commonly for the top part of the image in correspondence to the word sky.
Right.
Because that's usually where that is. But this part, it works very well for some types of images. And for this type of image, we're always kind of looking at the ground unless we're looking up to the distance. So there's not really that much variation spatially. So how much the attention map actually makes a difference is kind of questionable for this kind of data, but it can be very useful in other kinds of data. For instance, like looking at a face. Usually the eyes and the nose are in a particular place in relation to each other. With conglomerate rock and cross-bedded rock, that's not necessarily true.
Right.
Yeah.
No, that makes sense. This is really cool.
Yeah. So in addition to having the benefit that this could be useful as like a summarization technique to overcome the data downlink limitation, we could also use this here on the ground because we have already collected a lot of rover imagery and we have this huge database like from MSL. And if you're a geologist searching through this database for a particular type of image, then that really relies on having quite a bit of background knowledge already about where things are. And so we can make these databases more searchable, just like Google with the internet, by captioning them and then enabling you to search on the captions.
Right.
Yeah.
That makes sense.
Yeah. So that was also part of our technology demonstration. And we made this beautiful front end called Uhura, where people could search over the high-rise imagery. So high-rise is an orbiter, and it takes imagery of the Mars surface. And so we used like this map of Mars, and that was in the background of our Uhura interface. And then you could search for a particular feature and then see on the map where on Mars the rover had seen that feature, and then also get back all of the images.
Right. Very, very cool. So I think you said that this was also used for navigation. Now, is that just hey, it's firmer over here than over there? Or does it actually look up into the distance and say, I want to go where it has these features and not those features, like further out?
So this particular algorithm is not really used for navigation.
Okay.
It's used more for science. But one thing that it could be used for in terms of navigation, for instance, on the Fetch rover, where it's just driving pretty far distances and collecting samples, and we don't send it as many like commands, like all of the other rovers, we have a planning phase and we send it commands about where it should go for the next target. This kind of a model could enable something like a drive-by science where you tell the rover, like, hey, if you see any holy rocks, drive to that and get a sample.
Yeah, or rocks of a different color. Right.
Yeah.
That may be different makeup than what we're currently seeing. Yeah.
Right. Or, as you're driving by to your target, take pictures of that thing and send it back.
Right.
Yeah. So it's not as necessary for autonomous navigation in terms of like just helping the rover get around and making sure that it drives efficiently, but it can be useful for science navigation, or potentially like alerting a scientist like, hey, you haven't looked in this area, but you told me that you were interested in this thing.
That makes sense. I guess one other question or two other questions then. So it doesn't tell it where to necessarily navigate to. It's mostly telling it drive on this surface and not that surface. What if it doesn't find an ideal surface? Does it just kind of pick the best thing, or will it actually backtrack and try and go around?
With the Spock algorithm, I don't actually know if it will try to backtrack. I think that would only happen in like a hazardous situation.
Right.
So we do like optimal route planning, and that just optimal in terms of what is already there. That doesn't mean it's always the best path or like the most desirable thing to drive on. But out of all of the things that you could drive on, it can tell you this is the best path for you.
I gotcha. So essentially, somebody at NASA is going to tell the rover, hey, we want you over there. And then as it's going over there, it's going to look around and say, okay, better off driving over here than over there to get up to where they told me to go.
Exactly. So we plot targets for it, but that doesn't necessarily mean that we have to plot its entire course with this algorithm.
That's awesome. So I'm wondering a little bit about kind of your data collection and things like that, because as you mentioned, you can't send a ton of data back, right? And Mars is kind of far away. So what do you base your training your algorithms on?
Right. So at this point, we actually do have a ton of data from the MSL rover because it's been driving for many years at this point. So although we can't get all the pictures that it sees as it's going, over time, we have quite a bit of data.
Okay.
And now these deep learning models usually require quite a bit of data to train them, as probably your listeners know.
And to test them.
And to test them, yes. But so there are a couple of ways we overcome that. One is we use transfer learning, which I think most people who are familiar with deep learning will know about. So that's basically where you take a model that is trained on a very large known data set, such as like MS Coco or
Mhm.
ImageNet. And then you retrain it on your own smaller data set to learn the specifics of your data. Now,
Right.
these deep networks, they're early down features that detect things like edges and circles and curves. Those are all very good from MS Coco or ImageNet.
Mhm.
And you don't really need to retrain those lower down layers. You just retrain the up layers, the things that are closer to your
Mhm.
classification layer in your network that are more specific to your data. So what we did is we actually had to annotate images ourselves. So we had a geologist who taught us how to annotate images with the geological features we were interested in. And we had a bunch of labeling parties where we'd all sit down in a room with some pizza and chat and write captions and click, click, click,
Wow.
it was not the most exciting part, but it was definitely very cool and of like
Mhm.
one of the most important parts, right? And now our geologist, her name is Vivian Sun, is super amazing, and she is just insane. And one day decided to just label a whole bunch of images, and she labeled like 3,000 images for us.
Oh,
And
wow.
that was what we ended up using as our training set for the Scotty model. Now, in the Spock model, people can actually contribute to that and help make it better. So we have a Zooniverse project called AI for Mars, where people can go in and help us label Mars imagery with things like sand and rock and help rovers learn how to drive safer. So this is zooniverse.org/projects/HIRO-ONO, your Ono, AI, the letter number for Mars. I'll send
AI
you a
for
link.
Mars.
Yeah.
Yeah. Yeah. Because
So you can be a
I definitely,
scientist too.
yeah, I didn't type that in right. So yeah, go ahead and
Yeah,
send me the link.
I
But
will. And
I
then
didn't even
Hero
know
and
that
I
this
are,
was a thing.
yeah. So Zooniverse is really awesome. It's a platform where scientists can put up large data sets and citizen scientists can help them label it. And that results in some useful research.
Mhm.
And the premise with Zooniverse is that all the people who are putting that data up there are people who are researchers and are going to publish papers using the data that you help contribute to.
Right.
Or in our case, we're going to put them in space.
You're going to put my work in space. Awesome.
Yeah. So it's not out yet, but Hero and I are also working on generating a Zooniverse project for our image captioning model, where we can have people help us contribute to that one as well and caption some images. So be on
That's
the
cool.
lookout for that in the whenever future. It's a lot of bureaucracy we have to get through first to get there.
Yeah. So, folks, if you want to tell JPL what Mars looks like,
that's right.
very cool. I'm really digging this. This sounds like fun.
Yeah, this is by far like the highlight of my whole career.
Oh, I'll bet. So what's the best part of working on a project like this? I mean, it hasn't gone to space yet, but
right. It hasn't gone to space yet, but the best part of it is like seeing it run on our Athena rover. So we have a little rover that we use in the Mars yard, or we take it out into the Arroyo outside of lab and test it. And just seeing it run live in our little desert is just so cool.
That's awesome.
And then I guess like the other greatest part is when you show something like this, when we showed Uhura to the scientists and they're like, where can I use this? This is amazing. This is helping me.
Oh, absolutely. Yeah, I think that's something that most software developers run across is it's one thing to write the code and that it's fun, right? The discovery process is fun, right? But then to see somebody actually go, this really made a major difference for me.
Exactly. That's the part that gives you just so much satisfaction.
Yep, absolutely. Very cool. I guess one other question that I have is, let's say that we have some data scientists out there who's going, you know what? I'm tired of doing facial recognition and I want to go do Mars rover stuff. Like, how do you get a job like that?
So JPL does post openings on their website. And so you would apply through their website. And then, a good way is always to get in touch with a person who does this kind of stuff. I think most people, if you ask them to talk to you about their work, are just so excited that somebody else wants to hear about it that they're usually pretty willing, if they've got time, to discuss. So if you're looking at like a particular group, a lot of times NASA does have on their website somewhere listed that the people who work in that group and what they work on and their specialties and areas of research.
Yeah, that makes sense. It's funny because I wrote a book on how to find a job as a developer. And that's one of the big hacks that I give people is just like, hey, if you want to work at a place, go meet the people that work at that place and talk to them about what they do. And in your case, I can just tell that you love talking about this. So it's not even like, so what's it like to write algorithms for the Facebook feed, right? And there's going, well, it's not that interesting.
Yeah.
But it's you kind of light up when you talk about your work. And so
most
I can imagine
who are scientists, we just love talking about what we do, and we're excited when someone actually wants to hear about it.
Yeah.
My mom and dad are like, oh, not this again. So there's somebody else that I could tell about how cool this is. It's always great.
I love it. Did you know? Pass the turkey.
Yeah, exactly.
Very cool. Well, is there any other part of this that we didn't talk about that people ought to know?
No, I think I already gave an exceptional rundown. If people are interested in learning more, we did publish a couple of papers, and so you can read our research papers. Maybe I'll send you links. I don't know the best way to give that to people via a podcast.
Yeah, just send me the links and we'll put them up.
Okay, great.
Cool.
Yeah, if you just Google for Spock and Scotty, you might not find our research papers. There may be other things that you find.
Yeah. So if people want to reach out to you like on Twitter or something, what's the best way for people to kind of find you and follow you?
I'm not really a Twitter person. So the best way is probably for them to reach out to me on LinkedIn and to look for Annie Didier on LinkedIn. And I can send you a link to my page as well.
Awesome.
Hey, folks, I don't know if you've noticed, but I've been working a lot on figuring out how to help people become the most valuable developers on their teams or becoming the top 5% of developers in the field. If you're looking to level up, figure out how to contribute more, get the career you want, get the career that you want that will support the lifestyle you want, then you should check out the Most Valuable Dev Summit. I've invited some of my friends across the community, people that you've heard of, people that have worked on systems that you use on a daily basis, people who have invented new ways of doing things over the years in programming, and I've asked them one question, and that question is, how do you become a top 5% developer? How do you become 1 in 20 of the best developers out there? And so we're going to go ahead and have that conversation with them in interviews on the Most Valuable Dev Summit. And you can find that at summit.mostvaluable.dev.
Yeah. All right. Well, the last segment of this show is picks, and it's just shout outs about stuff that we're enjoying. I think I have an obligatory shout out to The Martian just because it's a fun and terrific book. And some of the things you're talking about having to account for are things that I think the author was Andy Weir.
Yeah.
He accounted for in some of the stuff that Mark Watney deals with. So yeah, I'm going to shout out about that just because I really enjoyed the book and the movie, incidentally. But as in all things, the book was better. Then I'm also going to shout out about what was it I was doing yesterday? Well, I did get a new phone. I did mention that. And the place that I got it, there's a website where they kind of rehab phones and then sell them because I never buy the new iPhone. I'm cheap. I never buy new cars either. But what I did is I was just looking for kind of used refurbished phones, and I found a page called Back Market, kind of like Black Market, but without the L. So it's Back Market. And they have technicians all over the US that get old phones and refurbish them and then just sell them through their marketplace. And so I got an iPhone 8 Plus, which is an upgrade from my iPhone 7 Plus that I had before.
What did your daughter get?
She's getting a lesson in not being so dang entitled. That's what she's getting. But anyway, so I found it on there, and I was looking through like classifieds because that's how I've gotten my phones before. And these cost about the same, but they give you like 90-day warranty and
that's pretty nice.
Good deal. So I was pretty happy with that. So I'm going to pick them.
I'm always a little skeptical buying from like a classified from a person. I'm like, what if you dropped this in a pool? Like, I just have no way of knowing that it's going to work for at least 90 days.
Yeah. Well, I haven't ever had a problem with that, but
good.
Yeah. And usually you can turn it on, and the iPhone does have some diagnostics you can run before. Yeah. And so I usually do that before I buy it. But yeah, here they just mailed it to me.
Nice.
She was super excited when she brought it in because she went and got the mail.
Oh, yeah. This is mine, right?
Yeah. And then one other pick that I have, and this is something I've just kind of been geeking out on lately, is Monday.com. So Monday.com is kind of a task manager system, project management system, but they've got templates for like CRM. They've got templates for all kinds of stuff, right? So I'm using this for the podcast management process. I'm using it for sales, for the Dev Influencers Accelerator. I'm using it for sponsorship sales. I'm using it for, hey, I want to keep up on people. My short-term planning, I use a system out of the book, The 12-Week Year. And so I've implemented that in there. And the thing that's nice about it is that you can build in all the automations for stuff, right? So I'm currently working on my 12-week year template, but essentially what you do is you set like 3 or 4 goals that you want to accomplish within 12 weeks. And then you come up with tactics, right? So it's, I want to make so much money. So then it's, well, I'm going to sell this and I'm going to build this product and I'm going to, right? And so you kind of get some of this stuff together. And then you have like daily or weekly tasks, right? And so when I fill in those tasks, I'm going to do this every day, right? Then when I put that task in, then it'll automatically populate all week 1 through week 12 with all of the proper tasks with the due dates. And so then as I go through it, I can just mark them off. I did this one. I did this. I did this. I did this. I missed this one. And yeah, because part of it's the accountability. So what they tell you is if you get 80%, right? So 4 out of 5, you check them off, then you're making enough progress towards your long-term goals to be able to achieve them. So
that's
anyway,
cool.
But the other system, and I actually paid somebody to help me with this one. When somebody schedules we're putting it in place like this week, but when somebody schedules an episode now, it'll shoot off an email to them and say, hey, here's the document where you can put all the information in for us to prep. We're going to send this to the hosts in a couple days. So a couple days later, it emails all the hosts and says, hey, here's the prep doc. Make sure you're ready. And then a week before the episode records, if you record more than a week in advance, because sometimes that does happen, where it's like right on top of it, right? And so then it just sends it to everybody. But then it's, hey, go review the document. Make sure you're ready to go. Make sure there aren't any more questions you need to put in there. And right. And so it does that. And then after it's done, when it's recorded, then it notifies my VA. She goes and finds the link for the editor to go download the files, puts that in there, and then it notifies him automatically and says, hey, there's something to edit, right? And so it just goes through the whole process, but it automatically notifies people every step of the way. Okay, now it's your turn. Okay, now we need this. Okay, now we need this. Okay, now we're, and it's just been really, really powerful because we've had to kind of keep track of it on our own up till now. So yeah, Monday.com is another thing I'm going to shout out about. And I love this stuff, so I nerd out on it. I'm like, what else can I make it do?
Nice. I actually pulled it up right now and it does look pretty impressive. I might have to start using this too.
Yeah. Well, I'm using it for a bunch of personal stuff too. One of them is just personal follow-up, right? It's like, hey, I want to check in with these people every week. And it's not that I don't care enough about them to check in on them every week, but I'm busy and I forget. And
Yeah,
so
it's
it's
nice
like,
to have the reminder.
hey, dummy, call your brother. So anyway, do you have anything you want to shout out about on the show?
Nothing that I can think of on the spot. Sorry.
Nope, it's all good. Usually, if people can't think of something on their own, I just ask, what TV shows are you watching these days?
Oh,
Or books that you're reading is another one.
yeah. So I actually just started reading this really good book called When Breath Becomes Air. And it's a book that I would recommend reading if you are in a good mental state, because it's by this neurosurgeon who ended up getting cancer and passing while writing this memoir. And so he's detailing the things that he has seen come through his practice and his own confrontation with his illness and like what makes a life meaningful. And it's very interesting because he's also able to come at it from this scientific perspective of how our brains work and how our brains construct meaning. And so that has been a really good book that I started reading recently.
Nice. All right. Well, I'm going to go ahead and push us toward finishing. It sounds like I have so many things to do and I want to go read the book now. Anyway, but yeah, thanks for coming. This was really fun and really interesting.
Me. I was very excited to talk about this. So this was great. I really appreciate you having me on. And I hope that everyone now is going to get pumped about Mars and about computer vision. So it's been an awesome experience.
Yep. It's been so fun. Thanks again. And we'll wrap up here, folks. And until next time, Max out.
Bandwidth for this segment is provided by CacheFly, the world's fastest CDN. Deliver your content fast with CacheFly. Visit CacheFly.com to learn more.